It is my pleasure to open the second session today. And the first speaker will be Professor Whitesides from Harvard. And I looked at what our small booklet says, and I read here that his current research interests include physical and organic chemistry, material science, biophysics, water, self-assembly, complexity, simplicity, origin of life, dissipative enzymes, affordable diagnostics, and soft robotics. So I ask Dr. Whiteside, does your day have 36 hours or a little bit more? He said, no, I just have good students. Well, I think it's a little bit more than that. It's my pleasure to introduce Professor Whitesides, and his topic is molecular recognition in water is different, the hydrophobic effect, and enthalpy and entropy compensation.
Excellent. Well, I'm delighted to be here and to congratulate the State of Israel for its success in surviving this long. I say this because I consider you youngsters, as it were. I mean, I was born in 1939, so, 70 is, it's okay, but wisdom has not yet really come. But both of us have a pulse, as it were, and it's always a pleasure to be here and to see the enthusiasm and the chaos that I think of as being an intrinsic part of Israel. So I'm going to talk about water. And it's like so many things in life. You look at it, and it's the most ordinary of substances. I mean, why would anyone spend time talking about this? And then you look around and you find people, and they're pretty ordinary too. And I point out first that they're very interesting, and also they're filled with water. And so why is that? And I really want to talk about a part of that problem. So much of science is based on the fact that what you see when you look may seem ordinary, and the most ordinary things are often the most interesting things. And water, to me, is one of those. So let me share with you some of our current enthusiasms with a subject which is beginning to make progress now, I think. So I'm going to start by showing you something that you're completely familiar with, which is a kind of picture that you would find in any biochemistry or chemistry textbook of a protein. And this is one we're going to work with, but that's semi-irrelevant. The point that I want to make in that is that you get conceived, we all get deceived by the pictures that we see. So the picture is not reality. Proteins do not exist in field-free space, and life does not occur in a vacuum, and that what we're missing in all of this is the water, because proteins and life exist only in water. So what is the interaction between them? And it's very complicated in very many ways, and I'm going to talk about only a small part of it. Let me begin by reminding you of a few of the things that characterize water. And I should say that we're fortunate to have Jerry Richmond here, who's going to talk later in the week, and she is an expert in a way that I am absolutely not in some of the most important physical chemical characteristics of water. But let me just give you a sketch from an organic chemist's point of view. Everyone is familiar with the high polarity and dielectric constant of water. But then there's some things that may be less obvious. One of them is, of course, that water is a hydrogen-bonded liquid. That's obvious, but what's not obvious is that the networks of hydrogen bonds that are formed, so important in ice, so important in maintaining the boiling point, are also critically important in other aspects. And one of the key things that's emerging now with water is the importance of these networks of hydrogen bonds. So that's one of the things I want you to pay attention to. The second is that water is very small, H2O. And who cares? Well, you say you can pack a lot of water molecules in a small volume or in a volume. That's fine. The concentration of water in liquid water is about 55 molar. Why is that important? And that is important because you can rearrange those molecules in lots of ways. And that means that water is unique in its capacity for showing entropic effects. Chemistry, or at least organic chemists, are very good at talking about energies, enthalpies, but actually pretty non-intuitive when talking about entropies. And it's one of the important and interesting aspects of this. And then a third problem is, or third issue is it has a very high surface tension. And the high surface tension is obvious from looking at the, whatever it is, a lizard galloping across the water there. But it's also important in the sense that what it says is that wherever there's a water nonpolar interface, which could be water or the active site of many proteins, something is going on which is unusual. The water there is higher in energy than just the ordinary water, higher meaning less favorable. So those are the three things that I want you to pay attention to. There are other things like the heat capacity and the cohesive energy density and a number of others, which are also unique to water and important in this aspect, but I'm not going to spend time talking about them. Now, what are the motivations for working in this subject? And let me give you two classes of motivations. The first is, if I can say it, just intellectual. So I would argue with you that molecular recognition is the single most important, most fundamental reaction in biochemistry, because signaling, structure, and catalysis all can be thought of in terms of one or another manifestation of molecular recognition. So we'd like to know how molecular recognition works. And organic chemistry has had a long and very successful period talking about molecular recognition largely through hydrogen bonds in methylene chloride and things like that. Part of the justification for that was that these studies in a simpler system would teach us about molecular recognition in water. It hasn't very much, and the difference is probably water. So molecular recognition we're beginning to understand, but molecular recognition in water we don't understand very well at all. So that's one part. The second is that if you look at different forms of molecular recognition or different interactions leading to molecular recognition, many people will pick a number, and I'm not going to argue this one way or the other, that the most important interaction holding things together is the hydrophobic effect. That is the interaction of nonpolar surfaces with one another in this very polar liquid. Now, the 80% number is neither here nor there, but the core of proteins, much of hydrophobic drugs interacting with hydrophobic active sites, lipid bilayers, these are all manifestations of the hydrophobic effect. So we are particularly interested in the hydrophobic effect because, among other things, it has no analog in conventional organic chemistry and organic solvents. And then the third very important practical thing is that we can't model the interactions between proteins and ligands. Some very smart people have worked on this problem for a while, and we're still struggling. Now, there's another reason for being interested in this, which is applied. And that is that when I went to graduate school in 1960, the problem of the recognition of the active site of an enzyme for its substrate or ligand was a well-posed problem. And subsequently, pharmaceutical companies, physical chemists, a number of people have put in a lot of very clever work to be able to predict from knowing an active site what structure of ligand will fit in there. And basically, we can't do it. I mean, we just can't do it. It turns out, oddly enough, to be easier to model the folding of a protein, of a polypeptide into a protein, because that's entropically constrained, than it is to talk about the binding of a hydrophobic ligand at a hydrophobic active site. And so why is that interesting and important? And it has to do with two people. First, we have Mr. Fisher, looking very stern with his glasses there, who introduced an idea, which was lock and key. And in the lock and key idea, you have, in the protein, you have a hole, and it has a shape, and then you have a key, and that's the ligand, and the ligand fits in the hole, and if the two fit, then you've got a start on how things work together. It's complementarity in physical shape. This is another one of my heroes. This is Mr. Kuhn. And Mr. Cohen makes a very interesting point. For those of you who are students and haven't read Mr. Cohen's book, you should take it off the web and read it because it's very useful. Mr. Cohen makes, among other things, the case that about 98% of the work that's done in science is making sausage. That is, it's basically doing better what has been done before, but doing it again and again and again. But that occasionally things come along which really the scientific community comes up with good examples. And Cohen was a physicist, and his example, of course, is quantum mechanics. But his point is that the scientists are just like everyone else, and we're, intrinsically slothful and lazy. And we only do something that's hard work, like coming up with a different idea, if there's a clear failure in our current intellectual paradigm. And you have a failure when you have a generally accepted idea, like lock and key, which simply doesn't work, which it doesn't. So what are we missing? And the argument that I'm going to make to you, and this is certainly not my argument, a large number of people, led interestingly by theorists, have suggested that what we should do is to consider this not so much lock and key as the lock is filled with water, the water is energetically unstable with the bulk, and that what forms the basis of the association of a ligand with a protein is the release of this energetically unfavorable water. So that's the basis of what I'm going to be talking about. Now, let me say a few things about molecular recognition, specifically in water, protein-water ligand interactions. I'm going to talk in a moment about delta G0 equals delta H0 minus T delta 0, but I would like, for my own peace of mind, to ask for audience participation, if I might. How many of you have actually had a real course in thermodynamics? Not the 2 weeks in, it's actually, oh, this is terrific. This is the reason I like to come here. There still is such a thing as physical chemistry here. I tried this experiment a year or so ago in a physical organic symposium in honor of somebody, Sam Stoop. And it turned out that of 150 people, there were 3 who had a course in thermodynamics beyond the 2 weeks that you get in freshman chemistry. So I feel very comfortable and at home, and we can talk about entropy and enthalpy, and this is all going to be good for everyone. One of the questions that we need to think about is what is the relation between water and solvation and entropy and networks and so on. And the only way I know to get at that are through thermodynamics experimentally and through simulations in theory, doing things that way. But, and this is an important issue, the theory has to have a large statistical mechanical element, because what one is dealing with is the properties not of an individual water molecule, but of a group of water molecules. Hence, one has to think about ensembles of states. The second thing is, I am interested in the hydrophobic effect, but there's a particular manifestation of the hydrophobic effect, which is, I think, finally becoming clear. And I'll explain it as we go along, but that's entropy-enthalpy compensation. And it's been quite a mysterious effect, but it's actually very important in a real sense. Now, there are a bunch of other things. I'm going to be talking about a particular kind of protein, but there are proteins that are plastic, so the motion of the protein is very important in thinking about how things fit together. And there are just a wide variety of different things. I've simplified it as much as I can for our research. I'm not going to give you a final answer, but I think I will tell you some things that are worthwhile knowing about the hydrophobic effect. So let's start with what I think is really the leading part of this story, which is people who do theory. And there are a wide number of people, starting from Kautzman and Tanford and Byrne and people like that, but Peter Roski and Lazaridis and Byrne, Freezer, a whole bunch of others, McCammon. If I've left out your favorite theorist, I apologize, but it could be a long list. And all of these people have in one or another way arrived at the conclusion that the networks of hydrogen bonds in water are an important part of the properties of water. And they take different treatments. I'll show you what some of these things are. But even with that, it's very useful. And then there are a group of people, some of them open source and some of them companies that are beginning to work on simulations for these. These simulations tend not to be of the class of molecular mechanics, which is basically an amazingly well-working set of bed springs. You just have things that vibrate and interact with one another. And rather they tend to say that in water you have many, many possible arrangements of hydrogen bonds. They're all talking to one another. They can have different free energies, but the different free energies are not necessarily different energies. They are different enthalpies. They may be different in an entropic sense as well. And so some of these, as I'll show you, are beginning to make real progress, but they're not there yet. And so the basic point that I want to make is one that I sketch here. And this is what we call in the group a water-centric point of view, that this ligand, hypothetically, binds to this active site, hypothetically, not by lock and key, not by complementarity in shape, but rather by the fact that the water here is free energetically unfavorable relative to water in the bulk. The water on the surface of the protein is also different. But then there's another layer of water around the ligand. When these come together, then the energetically unfavorable water here and here are both released to some extent. And it is that interaction that drives the hydrophobic effect, not entirely, but in part. And obviously, if they're hydrogen bonds or they're charges or they're things like that, all can be explained. But I'm talking primarily for simplicity about the hydrophobic effect. Now let me show you another one of those little oddities which has screwed up thinking for quite a long time. We're all familiar with this equation. Delta G is delta H minus T delta S in one or another form. It's always seemed to me like a funny equation because it's sitting here in kilocalories per mole, and what is this thing over here if I know what that is, and I sort of know what's that? I don't know. And I just want you to consider rewriting it, which is this way. I divide by T, and then it's all in units of calories per degree mole. And to a first approximation, this is a statement of the second law. And everyone has a favorite law. My favorite law is the second law, because the one thing about the second law is that anything happens follows the second law if it's a group of particles. So to an approximation, and this really is an approximation, but let me just interpret this for you. This is a statement of the second law. That is, if something's going to happen, the entropy of the universe, however it's defined here, is going to increase. We have an entropic term that comes from the heat that's released, other things, but the heat's released. The heat makes things vibrate more rapidly. It increases the entropy of the system. And then you have a term which is S, which is the entropy of conformation, of configuration, of all the other things that are there. So that this is a form of entropy, and this is a form of entropy, and this is this. Now you can say my interpretation is oversimplified, but it gives you a reason, among other things, for understanding that much of organic chemistry focuses on this term because a lot of organic reactions are exothermic. I mean, you put A and B together and the reaction gets hot. If you put a ligand in with a protein, it doesn't get hot. It's just a smaller effect. So that these entropic terms turn out to be more important here than they are in synthetic organic chemistry. So where did this start, the hydrophobic effect? And a good starting point was with Kautzman and Frank and Tanford and a group of other people who made the following argument, that you have water, here's water in bulk, you have two hydrophobic surfaces. Next to each of these hydrophobic surfaces, the water is structured. And the argument here is that, at least in this picture, the argument is that the structure is such that you're going to have a hydrogen bond pointing roughly away from the surface, and then this remaining hydrogen bond is going to be pointing as best it can in some sort of network here. And the reason it's oriented this way is that, after all, the oxygen can still interact through van der Waals interactions with whatever surface is there, and so that's the way it's going to orient. Now, Jerry Richmond can tell you variants on this, which make your head spin, but this is the starting point. And it's a nice, simple picture, and it says that You bring this and this together, these two hydrophobic effects come together because this red structured and hence entropically unfavorable liquid is released into the bulk. And it's, it's a very attractive and, to a good starting point, correct story. And it's based, at least in part, on some data. Now, for those of you who don't like thermodynamics, it's okay. We're going to come back to non-thermodynamics, but let me just show you a few data. This is ancient data, but it actually has some surprises. Look at the free energy of solution of methane to whatever this is, octane, in water. Free energy per mole is about the same, which is actually not intuitive what you expect. Now, why is it the same? As the alkane gets bigger, it actually gets to be more favorable to go in solution because the dispersion interactions, to an approximation, the dispersion interactions of anything with anything are always favorable. But at the same time, it gets to be less favorable entropically, and the argument for the less favorable entropically is that you're structuring water at the interface. And these two things happen to cancel out, and you get roughly a constant thing. So this illustrates the hydrophobic effect, but by the way, it illustrates something which has really been a frustration in this field for a long time, which is the compensation of an enthalpic effect, which we will interpret as being due to not just dispersion effects, but also forming hydrogen bonds, and then an entropic effect, which is also forming hydrogen bond networks. So, you get and you give away at the same time. So this is the classical picture. And this has been discussed by essentially every theorist working in this area has proposed a different, more or less, picture. And they're all in some ways related. So there was a picture which was iceberg kind of picture by Kausman and others, which simply says you form structured water around here. Stillinger, Chandler, some others have said that you can imagine this or think about this as being something in which, in order to put a solute in water, you have to, if I can put it this way, concentrate the space between the molecules. So you make a hole, and that's entropically unfavorable, and then you drop the ligand into that, and that's enthalpically favorable. So that's an approach to this problem. And then there's one that says the structure of water in here is very important, and there are others as well. So there are lots of different approaches to this, and I think they're all probably right to some important way. So what we're going to do is to work through some of this, but let me just give you a couple of orienting questions. The first is, in thinking about this, is this process of networks and water and hydrophobic surfaces, is it dominated by enthalpy or is it dominated by entropy? And I don't know any way of getting at that other than to do thermodynamics, calorimetry. And I don't know any way of taking the general audience and putting it to sleep other than giving them lots of data in entropy and enthalpy. So I'm not going to do that. So think of much of what comes after this as being an intellectually degraded version of a TED Talk with all the actual ideas left out. So the second question is that practically one very much wants to be able to take a lead and tailor its affinity, up or down, depends on the circumstances. We can't do that. We want to be able to circumvent H and entropy, enthalpy and entropy compensation. And this is it's a very interesting practical problem. We now have vast numbers of good crystal structures, and you look at a crystal structure with a ligand in it and there's a hole, and you say, terrific, I'm going to put a methyl group in that hole and I'm going to get tighter binding. And so you talk to your friends who are synthetic chemists, they put a methyl group there, they put it in, and you get exactly the same binding. Exactly the same binding. And even if it fits, it's exactly the same binding. So over and over again, you make rational changes in structure, and this has led to no change in binding. And it's been a dramatic frustration for the biopharmaceutical, or for the pharmaceutical company. And then there's a question I'm not going to touch about, which is, I say water as if it's one thing, but water freely distilled is one thing, buffer is different. Cytosol is somewhere between half molar and 1 molar in ions. I mean, it's a totally different thing, 30% organic stuff. Serum, active site is totally different than bulk. Protein outer surface, ligand surface. I mean, there are lots of different kinds of waters, and ultimately we're going to have to understand all of these things in some way. So why is now a good time to do this? And let me just sketch for you why there has been so much progress made in the last period of time. The first is isothermal calorimetry, and I'll show you a little bit more about this. The second is X-ray crystallography, and I'll show you a bit more about this. And the third is computational modeling, and we'll talk about that. So, isothermal calorimetry. Much of the thermodynamic data in biochemistry is widely disbelieved. And the reason is the older data were taken using the Van Hoff method, in which you measure, let's say, a binding constant as a function of temperature. The trouble is the structure of water changes, the structure of the protein changes, the structure of the ligand changes with temperature, and you have really no idea what you're doing. The effects are not big. You're making long-term extrapolations. The general sense was that this just doesn't work. What's happened is that it's now possible to do instead isothermal titration calorimetry, in which basically you can do everything at the same temperature. And for those of you who haven't seen it, what you do is to take a ligand and a protein, you put in drips of this. Each drip is followed by a giving off of heat. You add up the heats. Those give you the enthalpy of the reaction. And if you follow the way this works as a function of concentration, you can get the equilibrium constant. And if you can get the equilibrium constant and you can get H, then you can back calculate the entropy. And they're pretty good data now. I think that's okay. The second is what we call structure by FedEx. It used to be pretty hard to get X-ray structures. Now, we're not a protein structure group, but in the course of this stuff, we've probably done 50 to 100 protein crystal structures. And we do them by the intellectually demanding way of growing a crystal, diffusing in the ligand that we're interested in, putting in something that looks like a Turkish coffee urn filled with liquid nitrogen, and sending it to Brookhaven or to Lawrence Livermore. And particularly if you have a cooperating friend there, the next day they send you back an index data set, then that's all that's required. So you can't do this with neutroproteins, but if you have known proteins, you can get a crystal structure for basically everything. Now there's a particular issue that I want to make about this. This is the protein that we work with. It's called carbonic anhydrase, actually human carbonic anhydrase 2. And we've spent a lot of time working with this, and it has the characteristic that it is the ceramic brick of proteins. It is absolutely rigid. And at least this is now absolutely demonstrated with the backbone, and we're making good cases in showing it with the side chains. And what that means is that all the issues of protein plasticity, the protein changing shape on ligand association, just are not here. This is a rock solid thing, and the only thing that's happening is the ligand is coming in. So that makes it easy to do. And it has a bunch of other things as well. An important one is that anything that is a phenyl group with a sulfonamide binds to it. And that means that you can do what organic chemists like to do, which is to do experiments in which you look at sequences of compounds and look for trends. So that's all perfectly practical here. And a critical thing is that the quantities that you can get of this are essentially unlimited. Crystallization is easy. So it's really a very tractable study for physical chemistry. Now, what have we done? We've tried to simplify the problem further experimentally by doing the following thing. We say that anything that's an aryl group with a sulfonamide is a tractable subject, but it's not that tractable because there's a nitrogen or a sulfur or an oxygen or something here and here. And we've had even those are enough to confuse things. So that we don't look at these directly. What we do is to compare a molecule like this with a molecule like this. And what we've done in going from here to here is to add this benzo group over here. And the benzo group is a hydrophobic standard group. So that if we want to look at the hydrophobic effect, We just compare these two compounds. We've changed the surface area of the hydrophobic region, and we know exactly what we're doing. So we do this kind of thing. And by doing it, we've eliminated the conformational entropy of the ligand because this is rigid. We've eliminated the plasticity of the protein by working with carbonic anhydrase and all the rest of it, and we can now look at the hydrophobic effect in HS comp and so on. Aha! You felt that I was going to cheat you by not showing you data. But I'm showing you data, but in the grand spirit of thermodynamics, they're small enough that no one can possibly read them, so it's perfectly okay. So if you go through this series of things and look at these, and I'm happy to go through any of them that you like, what you find is that this extension from here to here, adding this much surface area that's hydrophobic, has a uniform property that it produces more binding, better binding, which is what you expect for the hydrophobic effect. But it does so by essentially entirely, through enthalpic effects. And this means that the sort of Kautzmann approach of saying you have structured water is not what's going on. It's something else that's going on. And not to be coy about it, what we think is going on is that you're changing water networks. So it is water, but not in the Kautzmann sense. But this is classically called the non-classical hydrophobic effect, and it turns out that it's about as common as the entropy-dominated effects. Now I want to summarize a couple of years of work in this picture over here, because it shows you what the interesting problems are. I'm going to talk about the binding of just the hydrophobic part, how much it contributes, in terms of two comparisons, since everything in thermodynamics should be done in comparisons. The first is to say that what we're going to do is to look at buffer as the standard, and then we're going to ask how these ligands partition into octanol and how they partition into the binding site of the protein. And when you do that, you find that there is a value of free energy here. So there's a positive contribution here of a couple of kilocalories per mole, and it's about the same for octanol and for the protein. However, if you look in more detail, you find that in octanol, this is entirely due to entropy. And if you look at the binding site of the protein, it's entirely due to enthalpy. So that you get the same effect, but it's for two totally different reasons. So that gives you an idea that you have to be at least careful in thinking about these things. And further, this is going a little bit ahead. If you look at simulations, and we happen to use mostly something called WaterMap, but other ones will give you similar kinds of results. What you find is that for the ligand and then the ligand with this benzoate appendage, they actually don't touch the surface very much. In fact, we have good hydrophobic effects where there's no contact with the surface at all. But what they do is to introduce changes in the network of water molecules that you can see around the edges. And those blobs are just the sort of 10% of the waters that you can see in X-ray crystallography. And even there, you're not really sure what's going on, but it at least gives you an idea of what's going on. So, the story is beginning to look as if the hydrophobic effect is due to changing the structure of water, not to contact between the ligand and the protein. So that's interesting. And quite useful in this particular case is that if you go through these calculations and you compare what comes out of the simulations, you can't tell the difference between the simulations and the actual experiments. They replicate one another. I don't take that as being more than a partial coincidence, but it's nonetheless a statement that things are going in the right direction. So that gives you a little bit of a feeling of the hydrophobic effect. What about entropy-enthalpy compensation? And for reasons that are not completely relevant here, we replaced CH bonds, which are hydrophobic, by CF bonds, which are believed to be more hydrophobic, or at least differently hydrophobic, but also have dipole moments. And we looked at a lot of them. This is quite a range of different compounds. They all have essentially the same binding constant. It doesn't make any difference. And if you look at why, it's not that they don't influence entropy and enthalpy. It's any time that there is a step in, which one is it? That's The center line here is G, so that's the binding constant. The upper line is H, so these are the enthalpies, and the lower line is entropy. So in every case, the entropy and the enthalpy precisely compensate one another. And we see this over and over and over and over. It's just a common feature. It's the rule rather than the exception. And computation can give some approximation of these kinds of things. The details are not important, but the computation is, and I'm going to come back to the computation and what it's teaching toward the end of this lecture. But you can also see some other really quite striking effects. For example, there would be an argument that would say, if we're changing water networks, maybe molecules that have larger volumes would do a better job. So we've compared phenyl and cyclohexyl and adamantyl. What you see here is entropy and enthalpy, and this is totally different from this, but in all three of them, you have exactly the same value of delta G because the entropy-enthalpy compensation is exactly the same. So, and it goes to show that there's something intrinsic here. It's not the surface area, it's something else. And the something else is more likely to be the character or volume of the water. So we're honing in on the picture that I showed here, that what's going on is not this interaction here that holds things together, it's the release of this water and the release of this water, or the rearrangement of these waters that provides the thermodynamics. So ligand binding is water changes, not lock and key, although lock and key determines the shape of the water. Then you say, all right, we've listened to all of this and you've been going on at some length, and we're very patient people, and it's a lot of thermodynamics, but you've been talking about just changing the ligand, and we're sensitive to criticism, and so we took the molecular biologist point of view, which is, when in doubt, don't think, do site-specific mutagenesis. And here are a whole series of things in which we've changed molecules in the active site, amino acids in the active site, from polar to nonpolar and small to large and so on and so forth, to ask whether this is just a peculiarity of the ligand. And what we find is what you see here. Here are all the changes, and it would take much too long to go through them. But the black line is the free energy. It's essentially unchanged through all these changes in up to 3 amino acids. And I forget which one it is, but these are enthalpies, these are entropies, and they precisely compensate again. So this is an effect which is common to the ligand, and it's also common to the protein. Now, there's an effect here which has been observed by others. And it's one of the few things that looks a little bit like a design rule, and that is that if you compare delta G here for this large number of ligands with delta H, it turns out that the contribution of the enthalpic term to all these hydrophobic effects is about twice the entropic contribution, over and over again. I don't fully understand that, but I'll come to it in just a bit. So the final story here of this part of things is that this is something where we should think about it as being water coming out. The water that's in here is what causes things to happen. And the picture is one that you see here in dissociation, which is it's the restructuring of water around these hydrophobic regions that leads to the dissociation. Now, let me begin to close up by talking about a couple of summary points to remember, and then a practical point about this, which will be of interest to all of you who are theorists and who can perhaps help. The first is that water near biological surfaces, water near any hydrophobic surface, is not like water in bulk. Now, Jerry can tell us more about what that means, but the thing that you need to think about is water, because of its networks, as having different free energies whenever it's close to a surface. And that means water's not water. There are lots of different kinds of waters, and it's not because the water molecules are different, it's because the networks that they form are spatially constrained, that is to say, entropically constrained, but that constraint shows up both in enthalpy and in entropy. So it's actually a pretty complicated problem. The hydrophobic effect as we know it is real, but it seems to be a non-contact effect. It's not that you bring the two hydrophobic things together. You can actually have them fairly far apart with waters in between, and you still see hydrophobic effects. And it has to do, again, as far as we can see, with the free energy of these networks. Docking does work sometimes. And if you look at effective potential functions in docking, some of them are pretty worrisome as to where they come from. I mean, I know the smog ones best, and they're pretty strange. But there's a question here, is docking working because it's causative, that is, you actually are fitting the ligand to the active site, or because it's correlative, which is the shape of the active site determines the water networks, and it's really the water that's making the difference. And I don't think we have a perfectly clear view of this. Computation is going to be critically important for this story. And the difference here is that the kind of computation that we're familiar with tends to focus on what are effectively free energy terms, which to some extent take entropy into effect. But for the programs that are specialized for looking at waters in cavities, they're statistical mechanical programs, basically. What you do is you do Monte Carlo runs. You set up a system, you let it run, and you see where the waters are, and then you set up the system again, you let it run, and you see where the results are. And so what's required is both potential functions, but also a lot of computer time. And for those of you who are interested in issues like networks and making networks as fast as you can make them, this is a very good problem to think about. Computation leads to this issue of entropy-enthalpy discompensation. I'll talk about this in just a moment. And then there's this final issue of who cares? And the answer is, at the moment, I think those of us who work on this for science care, but no one else does. And the reason is that in the pharmaceutical industry and people who do ligand design have been told over and over again that the revolution in computation is about to happen, and it's never happened. It's been 60 or 70 years now. And so everybody will be all over this as soon as we have the third, or we, the community, has the third or the 30th successful drug engineered this way. But that has not happened. Now, one last question. Where does this issue of entropy-enthalpy compensation come from? What's the basis of it? And there actually is a basis that makes pretty good sense. And that is, imagine that you have a Morse potential. And in Dunnett's and Williams' point of view, what happened is you brought a water molecule in here, or you could bring a water molecule in here. If it's in here, it's more tightly bound, but it's more restricted. If you brought it in here, it's less tightly bound. Enthalpy is lower, but it's less restricted. So, it's the usual interplay between entropy and enthalpy, or constraint and entropy that you see in many systems. Up here, the energy levels are closer together. You can have a broader distribution. So this will be less enthalpically favorable, but more entropically favorable. Down here would be more enthalpically favorable, but less entropically favorable. What a number of people have done, and the example that I give here is by Sharp, is to say that this basic idea is okay, except that what we're going to do is replace water molecule with networks of water molecules. We're going to calculate this using sort of stat-mech approaches, using some fairly simple approximations. And you find under those circumstances that if you get a bond energy of about 4 or 5 kilocalories per mole, then you expect entropy and enthalpy to more or less precisely compensate. Now, whether that's right or not is not important, because these are approximate calculations. But the fact is that you can come up with something that's about the bond energy of a hydrogen bond and come out with an answer that says that you should have, it is intrinsic that you will have enthalpy compensation is important. So the last two slides, we were asked to talk about some problems that remain to be solved. And let me just give you a couple of examples. The first is the one that's shown here. Until we actually can design molecules that in the hands of users make tight binders. Nobody's going to care because we've been through this before. It's harder to do than one thinks. We need to find ways of compensating HS compensation. Well, I just told you that it's intrinsic. How do I get around it? I don't know. Right? If it's intrinsic, it may be hard to get around. Deal with impossible problems. And the classic impossible problem is that it's very hard to drug, that is to find inhibitors that prevent two proteins from coming together. That's just a more difficult problem than it is to deal with cavities. And I think my hypothesis at this point is that the structure of protein surfaces actually means that the water that is hydrating there is more stable than it is in the bulk. And so that it's going to be hard to displace it. But I don't know whether that's true or not. Another question, are water networks idiosyncratic? Are there design principles? That is every one just a random accident, of shape and what it started from and the temperature and who knows what? Or will we be able to find principles? And the answer is we don't at this point know. What are the best theoretical approaches in simulations? And then what I've talked about has been a typical but atypical protein. Carbonic anhydrase is the same size as many proteins. It's perfectly standard. Every cell uses carbonic anhydrase. But having said that, it is so much more rigid than most proteins that what we've learned is not what you would expect. And then in this final slide, I want to raise a question that's related to what I've shown you. What I've said, in essence, is that we can begin to understand how this is all working, but ultimately we're going to have to rely on computer simulations. And it relies on something which is actually, I think, a very big question for science in general. I have no idea what these statistical mechanical simulations are telling me. That is to say, they do something, you do Monte Carlo, after you've done 1,000 of them, you end up with an end result. But like a lot of these things that I've listed here, that is, like some of quantum mechanics and certainly DFT. DFT gives brilliant results, but it doesn't tell me why it happens. The AI, the Internet of Things, all the rest of it, are basically statistical analyses. Genomics is statistical. Fast trading is statistical. Diagnostics is statistical. If we are ending up with a system in which what one has is lots of programs giving us lots of information, and the information is correct, but it's all statistical, what have we learned? And I don't know the answer to that. But this may turn out to be a problem of that sort. But in any event, what I hope I've convinced you of is that many of these problems, like what is the hydrophobic effect, what is entropy-enthalpy compensation, can we begin to understand where the weak points and the strong points are? We're finally, I think, over the hump, and it's now going to be up to you and your colleagues to figure out what simulations are going to get us to a point we can begin to make design rules. Thank you very much.
Can I ask about, over here, can I ask about maybe a more dynamical perspective on liquid water, which is, if I think of chemistry as a process, an event that happens dynamically, and then there's a dynamical response of the surroundings, I might guess that changes to the local structure of liquid water would have maybe biggest effect on some of the transport properties of liquid water. Breaking up a network seems to me would affect transport properties first and foremost. And I wonder if there's any merit in thinking along these lines.
I think the answer to that question is definitely yes. But remember, water, you already see it. I mean, water has a molecular weight of 18, and nothing else that has a molecular weight of 18 is a liquid. So you're already seeing an important characteristic. The high heat capacity of water is not a transport property, but it's an energy storage property. So I think that there are a number of things that you begin to see that are built into the water as we know it. We just don't compare water very well to methane, which would be a good comparison in terms of molecular weight and some aspects of structure, but not hydrogen bonding. So I think that re-looking at the properties of water and seeing what those properties have to teach us would be a very, very good exercise at this point.